Hello everybody, my name is Andrzej and this is a video abstract for our paper in navigation, a collocation framework to retrieve tropospheric delays from a combination of GNSS and InSAR. So GNSS and InSAR have synergic characteristics in spatial and temporal domain. And for instance, as you can see in this figure here, in the vertical axis is the time resolution, and in the horizontal axis is the space resolution. GNSS, which are the points in the red, they're quite continuous in the vertical axis, but not continuous in the horizontal axis. And the InSAR is the inverse, so continuous in the horizontal domain, but not continuous in the vertical domain. And moreover, GNSS are also absolute measurements, like from GNSS we can have Zenith Total delays, centimeter level accuracy nowadays, and from InSAR they are relative measurements because in synthetic aperture radar interferometry we're doing interferometry between two images. So therefore, this is exactly the research objective of this work, to combine or to exploit these complementary characteristics in a spatial temporal domain of GNSS and InSAR. Our combination technique is COMEDIE. So COMEDIE stands for collocation of meteorological data for interpretation and estimation of tropospheric path delays. This is a software developed at ETH Zurich, and it can do stochastic and deterministic of interpolation and screening of meteorological data. In collocation, the measurement is split into a functional part or deterministic part, which depends on some unknown parameters, a signal part, which we have modeled as a function of covariance of the signal, and this is the correlated part, what remains in the residuals, and the noise part, which is some stochastic uncorrelated noise that has remained in the residuals. For instance, here I want to share with you the deterministic part in case of GNSS Zenith Total delays. So Zenith Total delay is given as a function of Zenith Total delay at a reference position, some gradient in north and east direction, gradient in time, and also scale height for the height component. When we have InSAR difference delays, then we have modeled the difference slant delay as two difference of slant delays, which are directly modeled as a simple mapping function multiplying the Zenith total delay. And the peculiarity in this case is that we'd have to estimate two sets of parameters together. Our area of investigation for this paper was the Alpine region in Valais in Switzerland. It's an interesting area because due to high variability of the altitudes, we have also large variability of the refractivity index. This is a challenging area because GNSS is relatively sparse. And furthermore, we have also InSAR measurements here, which can provide interesting results about short-term components. Here I want to share with you only our real data results. So in the paper, we have also some extended simulation data result and the closed loop validation. But here what I want to share is, and what I think is interesting is two cases from the real data when GNSS and InSAR double difference slant total delays agree with each other, and when GNSS and InSAR double difference total delays do not agree with each other. So in this, in the first case, the combination lies somewhere in the middle of the two other solutions, and in the second case, it is interesting to notice that the combination follows more the InSAR results. And also, this is also verified when we see the full time series of GNSS, InSAR, and the combination for the three epochs. So the green curves follow more the red curves, which are the InSAR. Thank you very much for your attention, and if you have some comments or some questions for this paper, please do not hesitate to contact me on the email address shown in this slide. Thank you very much.